Hello YouTube, this is Cooking Components again. Today I'm back on the Keithley 160 digital multimeter. You see, I've got a lot of old caps, especially this one with the crack in it. And I got a bunch of new capacitors. So we can just start with soldering these new capacitors onto the main board and then try to find out if we get correct voltages and try to fire the multimeter up step by step to hopefully not burn up any components. But hey, this is cooking components. When components cook, they cook. First, I want to start taking a closer look at the components we already have. So these capacitors are from the axial leaded type. So the leads coming out of the capacitor are in one axis, in one line with the capacitor itself. So this is just a normal 125 microfarad 16 volt capacitor. This was not hard to find. Here is 150 microfarads. Okay, a little bit difference in the capacitance. 125 seems to be an odd number and not easy to find. But they are axial, so that's not a problem. Size seems to be the same. Only difference is they are rated for 36 volts, so they can take a lot higher voltage than the original capacitors. But I think that's just the development of the last years. I mean, it's an instrument from the 70s. It's old, so there are new capacitors to replace these axial type capacitors. The second type of capacitors are these white plastic casing electrolytic capacitors. They have 200 microfarads at 35 volts. And besides the strange plastic molded casing I've never seen before, they have an odd lead spacing. So when I tried to find capacitors with roughly the same shape, I couldn't get the same lead spacing. So I hope that the capacitors I've ordered will fit. Or, okay, they will fit somehow, but they should also look a little bit nice. So if I have to bend the leads in a strange way, that wouldn't look good. So here you can see the capacitors. They have the same diameter. They have not the same length. That's also a property I found is hard to get, the same length, because these capacitors are very lengthy. That's a property most developers don't like, because it makes it hard to get your PCBs in a shape that fits your casing. So because this multimeter has a lot of that space inside, the developers didn't seem to care, or they didn't have other options to get capacitors with other dimensions. So it seems that I've found a lead spacing that fits and a shape that fits. I remember it was very hard. And this is the third type of capacitor. It has a strange outer shell, some kind of plastic, or it even feels a little bit like Bakelite. And it's filled with an epoxy, I think, at the bottom to close it up. And also the lead spacing on this case is very strange, because I don't know if you can see it, but the negative lead is more to the side than the positive lead, or the negative lead is closer to the border of the casing than the positive lead. Also for that I got a replacement capacitor. This one here. Let me just get it out of the bag. So this has the same or a little bit smaller diameter. It's not as long. It has, where's the marking? Oh, there's the marking. It has the markings on the top. So it has 2200 microfarads, so 200 microfarads more. It has a lot of voltage more, so the old capacitor only went up to 15 volts, the new goes to 63 volts. I only took this high voltage because I wanted to get a matching case. If I would just have selected a capacitor with a close matched voltage, then I would have had more options and had options to go with a very small case. But since I wanted to match the case, I just got a higher voltage rating because that's how capacitors are made today. And the other difference is that the lead spacing is a lot smaller on the new capacitor than the old capacitor, so I will have to bend the leads somehow to get it in place. Now for the third type of capacitor. This one is a beautiful Mallory made in USA 50 microfarad 300 volt DC capacitor, which is, like you can read down here, a CAN negative capacitor. That doesn't mean it can do negative voltages, no. It means that the metal can of the capacitor is of negative polarity, so this is actually a contact. And it is a little bit special in that kind that this capacitor is constructed as an axial lead capacitor. So you can see one of the leads up here, and then formed into a radial lead capacitor by bending the upper lead down and then wrapping it in a paper shell and selling it as a radial lead capacitor. So this one is a little bit tricky because I want to a little bit preserve the style of this instrument. So I want to replace the capacitor inside of this shell. So I have two options to go. I can use an axial capacitor and try to rebuild the insides, or I can use a radial capacitor and just stuff it in there. So I just got two capacitors to replace it. This axial type and this radial type. And I will just try to figure out which one fits the best. So let me first try to get the original capacitor outside of its shell. Might only need to push. Yeah, it goes out. Oh, and there's a little paper spacer. And there you can see the axial type capacitor, and it looks a little bit like a battery. A battery with wire wrapping around its contacts. Okay. So this is the axial capacitor I want to try to replace it with. It has 50 microfarads, but it goes up to 400 volts, so should be okay. And I need to get the leads out like on this paper disc. So I need to feed the negative lead down the capacitor, and then the positive lead needs to go sideways a little bit, like on this one. So I'll just try to bend everything over. And hope not to break the leads off. So will this fit? Wow. This looks good. So only problem is that this capacitor is a lot shorter than the old one, but at least it's the same shape with the leads. Should be a positive. Okay, the casing has no outer marking for negative. So when you place it on the PCB, you just have to look out which lead is the one from the can, from the negative polarized can. Oh, no. There is, can you see this? There is an imprint on the bottom paper. So I can just use it as a polarity marking. Now I can see the polarity from the bottom. Okay, that fits kind of nice. Only the paper isn't laying down flat at the bottom. But I think there's not really something I can do. Perhaps I can grab a little bit of plastic foam. So I made two little pieces of plastic foam to fill the gap between the capacitor and the paper piece, so that it can lay somehow flat. So let me just shove this back into the capacitor. And now we have the paper backing pressed firmly against the bottom. Looks nice. And also the capacitor gained a little bit of height, so it's closely resembling the original capacitor. You might think to take off the plastic wrapping of the new capacitor, but I think that's okay for me. I can live with that. So next up would be putting all these pieces, all these capacitors back onto the PCB. So let me just start soldering the new axial leaded capacitors in. As a quick side note, I reduced the soldering iron temperature to 280 degrees C to not stress the PCB material too much. And also I'm using leaded solder because the solder type on the PCB is clearly leaded solder due to the age of the device. And I don't want to mix different soldering materials. So there is a marking on the PCB here and here where the positive terminal of the capacitors go. Only the negative terminal of the capacitor is marked, but the positive terminal is just on the other side. There are only two terminals on these capacitors. So let me just check how to place these capacitors, because we will need to bend the leads according to the holes in the PCB. So I'll grab my pliers and just eyeball it. One lead. And now the second lead. Yeah, seems to fit. Okay, the only thing I didn't think about is... Oh no, I have the right markings up. So this capacitor doesn't have as beautiful markings for capacitance and voltage like other capacitors have. For example, this one. So I got the right side up. Perhaps I could also just put the marking of the negative terminal up. It also looks a little bit nicer, or the Vishay logo. And this just looks a little bit ugly. I don't know how to say it. It looks a little bit ugly, the marking. But okay, that's how it is. Let's just bend the second capacitor. So I just decided for this capacitor that the negative terminal marking will be up. Just spontaneously decided this. Nice. So where's the positive? One positive is here. So the negative terminal needs to go to the other side. That's ready to solder. And for the other capacitor, the positive terminal is on this side. So the negative goes to the other direction. So for the upper capacitor, the negative marking arrows point to the right side, and for the capacitor down here, the negative terminal markings point to the left side. Okay, just need to solder it in. The range switch is somehow magically in the way every time. It just wants to be in the way. So I'm pressing against the capacitors and heating up the leads once more, so the capacitor sits flush on the PCB. Then we just need to trim our leads. And the first two capacitors are soldered. Nice job. Next capacitor. Which capacitors do we want to do next? I would start with the 4 little ones. I think they need to go into these holes. And also for them, the positive terminals are marked on the back of the PCB. So let's just put them through and solder them down. So they have also marked the negative side, the negative terminal, but it's not as obvious as on the other capacitors. Might even be... Okay, this looks like a negative marking, but it might be possible that these capacitors are non-polarized. I don't know exactly what I ordered, but I don't care. I'll just see it as a negative terminal. It won't be the positive terminal. That won't be the case, but I'll just use it as a negative terminal, or perhaps they are just non-polarized. That's possible too. So let me just take a quick look down. Okay, there are the positive markings. So these two, okay, they don't sit as they just sit very loose, so I just can't solder them in like the axial capacitors. I will need to somehow press against them. Okay, this looks like an acrobatic stunt soldering. Okay, at least the capacitor doesn't fall out like the other one just did. Are they straight? Yes, they are straight. So I can solder the other lead too. Still straight? No, a little bit bent. Let me just fix that. Okay, looks nice. So let me just cut the leads. And these two capacitors are also soldered in. So the other capacitors have the positive lead on the other side. So I'll just need to place them upside down. And I just noticed there's another way to figure out which terminal is the positive one. The longer one is the positive. The shorter one is the negative, as marked. So if I was not sure what needs to be the positive terminal, now I am. This range switch is just annoying. Oh, I think I need to correct the orientation of the capacitors. They look very, how you doing? Okay, straight now. Not exactly. One behind is a little bit bent. Maybe it's better now. Okay, looks close enough. Now the not so funny part starts. Getting these kind of modded capacitors in. Okay, the positive terminal of this capacitor is down. Positive terminal, the now longer one. Okay, that fits. Do I want the markings back or front? I mean, I can change it now. Will it be visible when I place it this way? This card belongs there. Not so good. Might be visible on the back side, so I'll leave it in its paper short as it is. So when I place it correctly, electrically correctly, then the markings will be on the back side. This looks very artistic. I need more solder. Okay, it's in there somehow. So is it straight? Yeah, looks like. Perhaps a little bit bent to the negative lead. Or to the positive lead. So I'll bend it to the negative lead. Looks good to me. Crimp the terminals down and we are done with this capacitor. Next up, the big fat one, and this might be a little bit more challenging because it has a different pin spacing. So positive lead is on this side of the board, negative here. So negative must go here to the other capacitor. Will I get it to fit? So there is at least strain on the pins, so they are now bent. Like you might be able to see. Not really, I think. Okay, perhaps I can get a better view later. Just push it down a little bit more. So is the capacitor straight? No, a little bit bent towards the other capacitor. I'll fix that. Now it looks straight. So let me just print these. All these capacitors look really nice. So these are our 4 new types of capacitors we replaced on this board. 2 axial leaded ones, 1 axial leaded one that we placed in a casing to act like a radial leaded one, and 2 different kinds of radial leaded capacitors. Looks very nice. Still has a little bit of a touch of vintage, but yeah, they are very modern capacitors. So I hope they will do their job here well. Before I can try to power this multimeter back up, I need to connect the back panel again, because the transformer and regulating transistor are mounted on there, and also the power jack is connected here. But for the power jack I don't have a matching connector, so I'll need to find a way around that too. So let me just try to find the route for the cable of the regulating transistor. I think it goes here. And then I think I should connect the power connections next, because they are hard to reach when the back panel is put into place again. And then there is the cable which connects the transformer back to the main board. That will go in now too. Okay, that's in there. And now I'll try to slide the back panel on again. Okay, I think I matched the screw holes. Cable was clamped under the switch for the voltage selection. Let me just get the screws back in. That's not going to work. Oh, I know you can't see, but at the moment I don't have a solution for that. Just believe me, I'm trying to get the screws back in. But I think the alignment is not correct. Okay, got the first screw. For the second screw, the alignment was not correct. Okay, I think that grabbed too, so I can show you a little bit more what I did. So I added these 2 screws, this one here and this one on the back. And I still need to tighten them up. So then there are the 2 connections of the analog out. And there's a ground connection coming from the transformer. So I think there are all connections made. I could just route the cable from the transistor a little bit nicer between these 2 connectors. And there is a small specialty I'm doing. Some of you might have just noticed this jump on my table. The power switch in front of the casing is connected via this connector under the transformer, and it's actually switching mains voltage. So it's switching the transformer off and on. Yeah. Even this is a very thin wire, and the insulation is even thinner. They decided to use this to switch mains voltage. Yeah, I think that's how you did it in the 1970s. So I don't want to use this while testing, so I'll just bridge the switch connection using the jumper. So let me just put the jumper in place. I hope you can see what I'm doing. There is this multi-way pin header. Actually, there are just two lines connected. And I'll bridge these two lines using this jumper when I can see where to place the jumper. Ta-da! Powered on whole time. And there are the two connections. So to power the device up carefully, I want to use a Variac, but because I'm trying this the first time, I'm going a little bit carefully on this topic, and I just realized that there is a potential hazard using these things. So I just connected a normal power plug to the transformer, and I connected a wire with some banana plugs to it. And when I turn it on, I don't know where live and neutral go to the transformer. So it's possible that you have live on the wire that's just going through the transformer. You regulate the transformer to 0 volt, but you still have 230 output on the transformer and can shock yourself. So I'll just try that now. Okay, you can see I can turn the transformer up. I can turn the transformer down. And when I now measure at the output, or I'll use the wire that is normally the neutral, you can see I get, okay, you can't see, I get 230 volts. I need something to put under my multimeter that I don't have reflections in. Okay. Regardless what I am selecting as output voltage. On the other hand, if I use the other connection, you can see that I kind of get a mirrored image. So I've selected a voltage that is close to the mains voltage, and when I measure between the live and the protective earth, I get close to 0 volts. So this is happening because the transformer is actually working between the wrong connections. So it's letting phase through, and it's regulating the voltage on the neutral line. So I need to turn the plug around to get a correct picture. Let me just do that. So now I have turned the plug around. So neutral and live are connected as they should. And you see on the face, I have the same voltage as the multimeter that's integrated, or the voltmeter that's integrated into the transformer shows me. So I can go from 0 to even 265 volts with respect to protective earth. And when I connect my multimeter probe to neutral, I also get 0 volts, despite what I am selecting on the transformer itself. So now I have a setup that's at least not directly killing me. And remember, don't do anything I do today yourself. It's dangerous, and you can't make me responsible for it. I warned you. So for everyone wondering what's this, I just added a safety switch so I can quickly disconnect everything. Or at least close to everything, because it's after the transformer, so the transformer will still be powered. And because there is an old kind of connection on the back for the mains voltage, I think it's called 163 connector. Couldn't find out more. It's used on old test equipment like this. And yeah, I'll need to get a little bit creative on connecting to the prongs. So I have these long kind of alligator clips to go onto the connections. And because now there's not enough space to get onto the earth connection, I'll just clip on the earth connection onto the screw here and make sure that it has connection, because this aluminum is coated, and so it might not be electrically conductive on the surface. So I'll check that this is connected just with the multimeter. Yep, that has good connection. So just in case you're wondering what I'm doing and how I am able to do this, I found the schematics and manual of this instrument online. It's easy to find, just Google it. And there's a page which describes where the voltage points are. So not only the voltage points for calibration, also the voltage points for the internal voltages. And I'll just slowly ramp up the voltage and check that the voltage lines don't go too high. And I hope it won't burn up on me. So the important voltage lines, as far as I can see, are this one. It's 3.6 volts. Then plus 15 volts, minus 15 volts. All of them are corresponding to ground. And then there is not marked on the PCB 210 volt line that's used for the Nixie tubes, I guess. That's a point where I will just measure on the capacitor. And yeah, I think that are all voltage lines we need to consider. But maybe there's more in the manual, I'll check. So let me just start. So the knob is on 0. I think everything is safe. I'll power it on. At the moment, nothing. So I'll just start to rise the voltage. Okay, there's something happening on the 3.6 volt voltage rail. Also the 15 volt. Nothing on the 210 volt voltage range. Okay, I'll carefully increase the voltage. I don't like to see that there's nothing on this voltage range. Maybe it's not referenced to this ground. So let me use both probes. No, still no voltage on this capacitor. Interesting. So I'll turn everything down and take a closer look. When digging around in the schematics a little bit, I found this side which describes the power supplies. And here's our 210 volt voltage range. And I noticed this capacitor. And this capacitor is the capacitor we saw in the beginning of the video, which is cracked. So maybe this capacitor killed this diode or this resistor that are in the circuit. There is no fuse in the circuit. There's only the transformer, the resistor, the diode, and this capacitor. And after that, we should have 210 volts. There is a list of the parts, and the resistor 209 is described there as 82 ohms and half a watt of capacity. And the diode 206, it's here. It's a rectifier diode with 1 amp and 800 volts. So we need to measure those two components and then find out if we have to replace one of these components or if the problem is with the transformer. So on the left side, we have the transformer connection. I'll just disconnect that. And then after that, we have a trace going from the transformer connection, which is now floating, to the resistor connection, and from the other side of the resistor through the diode, and through the diode to the capacitor. And then there is what I didn't show you, a 1 mega ohm bleeding resistor to discharge the capacitor when the device is turned off. So let me just check the resistance of the resistor. And that shows 106 ohms. That's a little bit high, but maybe in spec. I don't know exactly. And now let me check the diode. So there is no short, that's good. So let's switch to diode mode. So I think in this direction, positive here, negative here, we should have no connection. Nothing. And in the other direction, because here's the positive terminal of the capacitor, which should be charged. And here should be the negative. I should have no connection. I messed that up. I should have no connection in this direction. And I should have connection in this direction. But there's no connection. So let me just choose a higher voltage to test the diode. So the multimeter now not only goes up to 3 volts, but to 15 volts. But a standard diode shouldn't have more than 1 volt of voltage drop. So it should have been possible to measure it. And again, nothing. And also in the other direction, nothing. So this diode is clearly dead. And that's the reason why the capacitor isn't charged. To take a closer look at the circuit, I have removed the back panel with the transformer again. Here's the circuit we are searching for. We have the transformer, the connector of the transformer to the PCB, a resistor with 38 ohms, a diode, the blown capacitor, and the bleeding resistor. And after that, it goes further into the circuit. So let me just try to find everything on the PCB. I placed a lamp behind it so you can see the tracks shining through. On this side we have the transformer connection, and on pin 1, 2, 3 there should go a trace off under this capacitor to this resistor, which is the 82 ohms resistor, through the resistor onto the diode, then through the diode and charge up the capacitor. After that, there's a small bleeding resistor which should discharge the capacitor after the device is turned off. So let me just start measuring. I can see that this resistor here has the markings gray, red, black, which would mean 82 ohms, and silver, which means 10% of tolerance. So this resistor is good when it has around 74 to 90 ohms. So I think we'll still measure 106 ohms. Yes. So there are two possibilities. One is that this resistor got a little bit of damage when the capacitor shorted. Or, I mean, this instrument is from the 70s. So this resistor is around 50 years old. Maybe it just aged a little bit. So it could still be okay, and we'll see later if the voltage drops further or not. I think the 210 volt voltage range is not meant to be very precise. You can see that on the fact that it has only a single diode for rectification. So it's not a very smooth voltage. And I think there is no regulating circuit on the PCB. So someone knew they wouldn't care about this voltage. And I think it's most probably used for the Nixie tubes for illumination. So they didn't care that it's very precise. So next is the 1 mega ohm resistor. And there we have a small problem. You see the capacitor charging up and the voltage, the ohms ranges of the multimeter changing. Yeah, first the resistance was rising, now it's falling. I think it will go to 1 mega ohm some time, but for bleeding resistor, I think our measurement is good enough. So next would be to check the diode. Let me just change to diode mode. So we would expect that this capacitor is charged with the positive on this side and the negative on this side on ground. So we can go with our multimeter to pin 1, 2, 3 and nothing. Okay, let's go closer to the diode. Still nothing. So this should be the direction the diode is conducting, but it's clearly not conducting. So this diode is dead. So let me just try to take a closer look onto these components. But I think you can tell, despite of some corrosions on the leads, there's nothing special to see around here. So no obvious markings of destruction on these components. So if I hadn't done my measurements, I would say these components are still good. That diode looks nice. Nothing to complain about. So I'll just start by desoldering the old broken diode. So where it is? Here it is. It takes a lot more heat than expected. I'm carefully soldering to not destroy the PCB, but somehow it's not taking the heat. And I see the PCB degrading, but I still have a lot of solder on the connection. I don't like that. Perhaps I need a little bit more than 208 degrees. Let me go for 300. And fresh solder away. Okay, now I see. I think they crimped the leads of the diode, so the lead outside of the PCB is a little bit thicker. Maybe I can show you that. Where's my diode? There it is. So this lead is pressed flat, so it's thicker than the hole. This may be why I have so much problems desoldering it, but I can just take my pliers and snip the bigger part off. Or I snip the lead on the other side, so I can show you how the lead looks. So the lead ends just fell out, and here they are. So the flattened part is not the part I just cut, it's the part that is soldered into the PCB. So that is why when I desolder it, it looks like it's still soldered, but it's just that the lead is so big that it doesn't fit through the PCB again. So they put the component inside, pressed the lead flat, and then soldered it. So for the new diode, I've got an, please focus. I got an 1N5408, which is rated for 1000 volt at 3 amps. Let me just try to eyeball bending of the leads. And I want to have the writing up. One end. And we might have a slight problem. I think the leads of this diode are too thick for the holes. Yes, they are. So I might need to get the drill out. And here is a 1.2 millimeter drill for the job. I hope the hole will be big enough. And now let's look if the diode fits. Nope, doesn't fit. So I just soldered the diode in again. Unfortunately, I forgot to let the camera roll. So the diode is now soldered in. Let's measure if our circuit works again. So I'll go to the positive end of the diode, so where the capacitor gets charged, and to the third pin of the connection of the transformer, and as you can see, I get a voltage drop of 1 volt. That's including that the current of my multimeter is going through the 106 ohm resistor, which should only have 82 ohms, but okay. So when I go to the diode directly, I even get a lower voltage drop. And on the other way, nothing. The diode is blocking. Beautiful. That looks like it would work. So I'll just put the backplane with the transformer on it again, and we could try to power it up the second time. So let me try the trying not to kill myself thing again. So I'll just yes, transformer is at 0. Let me turn on the power again. So we have 0 volts coming in. I'll turn it up slowly. Okay, we got 35, 36 volts going in. And I'll check for the high voltage line. Yeah, the capacitor is charging up. Nice. But from what I see, I'll expect that the capacitor will charge up much more than only 210 volts. I mean, the voltage is now higher than I would expect. It's higher than the mains voltage going in. But maybe that's due to that there's no load on that voltage rail. Could be. I mean, I don't know the turns ratio of the transformer, but maybe that's the reason. Still very low voltages on the other rails, but I expect them to be low because they also don't get the correct input voltage. So let me just slowly try to increase the voltage up. So we are about 93, 94 volts on the high voltage line. 6 volts at the 15 volt. -6 at the -15 volts rail. And 1.9 volt at the 3.6 volt rail. Okay. I think that's the input to the voltage regulators. Ah, yes, that's the input for the -15. That's the input. No? Okay, they both seem to be input for the -15. Then they might be both inputs to the plus 15 volt. That would be the input for the plus 3.6 volt voltage rail. Yes, that's our high voltage rail. Ooh. Should be more careful. Okay. $150 volt. 260. 3.2. 12.5. Negative 12.5. Okay, an input current measurement could be interesting, but I don't have one at the moment, so let me just get another measurement. So I just got more cables floating around on my bench, and we now have a measurement of the current going into the multimeter. So, and yes, it's AC current. So that multimeter is measuring AC current, and this multimeter is measuring DC voltage. Because on the PCB we expect to have DC voltages after rectification. So let me just slowly turn the voltage up again. I don't see current. Let me just check if we have voltages. We have voltages. So why don't I have currents? Maybe it is because the usage, the power consumption is too low. Okay, I'm not expecting that low current. AC current, 0. Interesting. So that lead goes into the correct terminal. That one goes into the correct terminal. What's happening? So it's at least in line. You see the bleeding resistor doing its work. It's bleeding off the excessive voltage. So let me put it in again. I don't see current. Interesting. Okay. Maybe I'll check the lower current range. Ah, he's warning me because I'm taking leads out. Why is that warning? Yeah, okay. What happened there? So there is current flowing, but it's only 5 milliamps. What are you warning about? Okay, so the current we have is too low for this measurement. AC true RMS. It doesn't get it. Okay, think I need to live with that. So the only way to find out if everything works is to just increase the voltage more. Okay, we are at 210 volts on the capacitor and only around 200 volts on the input voltage. So we have 3.7 volts for our 3.6 volt voltage range or power line. We have plus 15 volts spot on. We have negative 15 volts and they are a little bit off. So I think we should expect to at least have no wrong voltages which will kill our device or kill the rest of the electronics. So next step would be to install the modules again and then ramp up the voltage with the installed modules. And then we might see first if the device works and then if the 210 volt voltage range will be lower than it is at the moment. Because at the moment, when I turn the voltage up to get to line voltage, I think the voltage on this 210 volt voltage range would be too high. So let me just put everything back together, or at least close enough back together that we can do further testing. So as far as I could find out, this one is the analog board where every analog amplification is done on. Let me put this back in there. Also the cable. Then this is a backplane. This is called the tube board, which seems to do the analog to digital stuff too. And this board is called integrator board. So this board goes into the bottom of this backplane, but I won't put it completely back in because the tube board needs to go in there with the integrator board, and this this shaft needs to go through the board, so I need to put both boards. See how the shaft goes through? There. So these two boards somehow seem to need to go onto this backplane simultaneously. So I'll just try that. Okay, one board, two boards, gently pressing down. And they are not completely. The tube board isn't in. Now the tube board is fully in. As far as I can see, it's fully in. So I can try to get this back onto the multimeter main board. Are there any cable connection I left? No, I don't think so. Because this cable connection is back on. This cable connection is back on. This one, transformer, this board didn't have a cable connection. So I can put the assembly of integrator, tube board and backplane back onto the multimeter. Okay, that looks nice. I didn't put any screws in there. I might do this one. No, I don't do screws now. I don't do screws now. So I hope this looks good. And now I'll prepare to power it on again. So let me just try to power this on again very carefully. So there's the AC. Let me just measure. I got nothing. Oh. Safety first. Yes, 52 volt. 1.5. Ground. Oh, shoot. Wrong ground pin. Let me measure this again. 54 volt. 1 volt. 2.6. Negative 2.6. Oh, this instrument is not measuring AC. Now it's measuring AC. So 91 volts. 2 volts or close to 5.6 volts. One 145 volts. 3.8, 11, negative 11. Oh, I see glowing. I see glowing. So we have here 177 volt. 3.6 volts. 14.8. 14.4. So at the moment, I'm not trusting my current meter. I'm not trusting it. I don't believe that the current consumption from this device is so low that it can't be measured. I'm not trusting this multimeter. Okay, but okay, I can't show you at the moment the Nixie tubes, but believe me, they are glowing. Okay, perhaps I can show you. I know I should be careful, but I want to show you the Nixie tubes. There they are glowing. Something is happening, and it's even switching around sometimes. So they are not fully lit because the voltage is, I think it's too low, still too low, but at least something is happening. Okay, but I don't know why my current meter isn't showing anything. Really, I don't trust this multimeter. And I want to trust it. Damn. Let me just turn this off. Perhaps the switch is a little bit dicky. Still nothing. And the Nixie tubes turned on again. I can even feel through the gloves that the transformer heated a little bit up, but that could also be due to losses. Okay. I think it's time to switch the meters around. Give me a sec. Okay, as you can see, I switched the meters around. So I hope we will have a successful current measurement and will be able to proceed. Oh, instantly there's current. And is there voltage? Okay, at least the voltage measurement at this instrument seems to work. And the interesting fact is I tested this multimeter before, but I only tested it on DC, not on AC. Okay, then we can move on. Current seems to rise linearly. So no, it has an annoying beep on high voltages. Can I turn that off? I'm starting to hate this multimeter. Okay, I'm at 230 volts. That's nominal input voltage for this multimeter. I have 3.6 volts at the 3.6 volt rail. I have close to plus 15 volts at the plus 15 volt rail. I have close to minus 15 volts at the minus 15 volt rail. And I have 212 volt and on the 210 volt rail, which should be correct. So then let me just show you the completely lit instrument. So it's showing something. And it's consuming 106 to 107 milliamps, which should be shown by this instrument. What a bummer. Okay, then I'll turn it off. And then I think the next step would be putting everything back together and hoping that it works. So let me just start to put this together again. So this not fixes the PCBs in their height. And this one too. Hope I can get it back in there. That's the rod that keeps the PCBs in position. Some pliers. So then what's next? So these components are all in place. Then we might need the first part of casing. So let me just connect the leads again, measuring leads. I need to find out where to route these cables. The rest should be quite easy. Good question. Next question. Hmm, 6 millimeters fitting, 7 millimeters fixing. What's wrong? No way. Are you kidding me? I should remove that shot right there. This cable saw me an accident about to happen. 230 volt on that thin on cable. Ooh, that scares me. And I also don't know where this should be routed. So I'll let it hang there. How do I find out in which position the switch stands? Okay, perhaps it has a limit how far it can move. Okay, it has a limit. So it may be that it is now on nanoamps. But I can't screw it into this position, because then I can't reach the screws. So I'll just fasten the inner part of the switch mechanism. And then loosen the outer part. So I now brought the switch into its resting position on 100 nanoamps. I'll now correct the knob position. Okay. I hope the switch is now correctly set. Here comes the front cover. Okay. What was the front of this cover? Which way is which? So it got bumped on this corner. Perhaps I can find out. No, I can't see a bumped corner. Got bumped on this corner again. Nothing to see here. Okay. I'll just try to screw it on. Perhaps it fits. No, it doesn't. It does not fit. So the screws are offset. That's the way to figure it out. No, it fits. Oh shit, that's power cable. Power cable system insulation. Nice. Just cleanse it. Oh man, that doesn't look nice. Yeah. Beautiful, but it doesn't seem to have damage taken to the insulation. Okay, ignoring it, putting it back together. I'm just glad that the casing's ground. So at least the RCD should detect when there's a fault. Nice. I'll just need to test it. To power it on and enjoy how beautiful it looks. So let's find out if it still works. Okay, something is wrong. Or is it? It might just be the range. Okay. Looks good to me. Some of the letters seem not to be working correctly, but that might just mean that the instrument needs to heat up, warm up a little bit, and hopefully not burn down. So let me just check that it is indeed safe and there are no hazardous voltages. So I will just measure between ground or earth potential and everything I can touch. So I'm measuring AC and DC at the same time. Oh, there is a reflection on the screen of the multimeter. Okay. So on the casing, there's no voltage. On the negative connection, there's no voltage. And on the positive, there is no voltage. So let me just check between those pins. There seems to be a little bit. No, there's nothing. Okay. In DC mode. Nothing. Okay. And what happens when I switch over to the ohms range? There is a voltage, but that's to be expected because you need something to come out of your multimeter when you want to measure ohms. Okay, the mega ohm range. Ah, okay. Sure, the mega ohm range is measuring my multimeter. Okay. I thought it was broken, but not. Okay, let me just grab a resistor. Now that we know that it should be safe to the touch. Okay. Can't make that out, but I'm sure we are not in a range that we can read it. Now we can read it. 2.17 kilo ohms, I would guess. And that should be overload. Okay. So 2 point something kilo ohms. And it should be a 2.2k ohms resistor. I see that the Nixie tubes still seem to have a little bit of a problem. They don't look as clear as I would expect them. Perhaps I should turn the lights off to make the Nixie tubes more visible. Looks a little bit like 2.6. Oh, now it's going all over the shot. It's not really stable at the moment. Now it's stable. Perhaps the switch is a little bit crusty. but that was to be expected after 50 years. You see, I just wriggled the switch a little bit around, and now it has a steady state and close to the value it should measure. That's off. Oh, I'm missing a dot. There's my dot. You see, it's just the switch contacts that are not very good anymore. So they will need thoroughly cleaning. I'll do that later with contact cleaner and opening the case and wiping around and turning the knob and so on. But I think you know what I will be doing. So let me just check if there is voltage measurement. And I will just simulate voltage using my multimeter in diode test mode. Yeah, 3.24 volts. That should be expected. And I can change the range. 16.6 volts. It looks like. Yeah, that should be also the expected value. I could just load the multimeter down. Yeah, the multimeter shows 6.2 volts. The 160 digital multimeter also shows 6.2 volts. I think that's good enough for a 50-year-old multimeter that has not been calibrated since 2004. Okay, I think that wraps it up for today. Subscribe, comment, give it a like, all the good things. I hope you liked it. I hope you stayed till the end. And perhaps you learn something. Perhaps you will repair your own multimeter. Thank you for watching and have a nice day. Bye. Oh, current measurement. Yeah. 4 milliamps. 0 point something milliamps. Oh, that's too much. Oh, 0.7 milliamps. That's the current the multimeter is driving. Bye. And for the bonus content, I'm trying to open the broken capacitor. Ouch. that's glued in. Oh, what can I do? Wow, what a mess. Das ist nicht dein Ernst, dass jetzt die Speicherkarte voll ist.